All right, so 5.3 is called Finding Trigonometric Functions. Okay, again, we're continuing in that brown book, so this is out of the PDF that's on that module. The first thing, and we talked about this earlier in the week, but is that magical word that is Socatoa. So Socatoa is an acronym that stands for sine equals, the next two letters would be opposite over hypotenuse. Cosine, which is the C, goes with the next two letters, which is adjacent over hypotenuse. T goes with O and A, which means tangent is opposite over adjacent. So this is something you learned about in geometry. This is something that never goes away. The kids in pre-calc are still doing it. The kids in calc are still doing it. Socatoa is one of those things that will haunt you for the rest of your lives. If you could just learn how to spell that word, you're golden, okay? And this is for sure on standardized tests. I've never seen a standardized test that didn't have some sort of right triangle trig on there. So now if we just take those and flip them, we get the reciprocal functions. Cosecant would be hypotenuse over opposite. Secant would be hypotenuse over adjacent. And cotangent would be adjacent over opposite. So of course we mean these in relative to an angle. So if I actually had a triangle drawn, has to be a right triangle, and I put theta in the bottom left corner, then the side opposite it is literally the one that it doesn't intersect with, the opposite one. So this would be opposite theta. The one next to it, but not the hypotenuse, is the adjacent side. And then the hypotenuse is the one opposite the right angle. If I switch that, and I put theta at the top, now the bottom side is opposite. The side next to it, but not the hypotenuse, would be adjacent. And then the hypotenuse, always the one opposite the right angle. So depending on which angle you're talking about, the opposite's obviously going to move, the adjacent's going to move, but the hypotenuse is always the same. The hypotenuse is always the longest side. So if you have two of the side lengths and you want to find a third, you can use triples if they're a triple. So as a reminder, our triples are 3, 4, 5, 5, 12, 13, 6, 8, 10, 7, 24, 25, and 8, 15, 17. Those are the most common ones. It's not the only ones. Like 9, 20, 25 is also one. But those are the most common. So if you have two of the sides, you can use a triple to find the third side if it's in one of those sets. If it's not, then you use a squared plus b squared equals c squared. Which means a side could be a radical. Obviously, we simplify it if it is. And when we set up our ratios, we always rationalize. So those things you want to remember to do. So for me, when I if you go back to like the coordinate point ones where we had to like actually draw out the coordinate point and you could figure out r and you could do y over r, you could do y over x, there's a direct overlap between these. I could do y over r for sine, or I could do opposite over hypotenuse. They are the exact same thing. So whatever helps you remember it is what you obviously want to use. The only time you can't use those is on your quadrant angles, like the ones that are on the x-axis or the x-axis or the y-axis. Those you can't use. All right, so this one just says find the 6 trig functions. I've got a right triangle, 7 on the bottom, 24 on the left. What do we know is the hypotenuse? Which would be what? What would be that number? 7, 24, 25. If you don't know it, you've got to do 7 squared plus 24 squared equals c squared, and then you've got to solve it. Without a calculator, that's not going to be fun, so keep that in mind, okay? The triples are definitely going to help you. So now I want to do sine I want to do cosine, and I want to do tangent. I'm going to put theta here. So we're going to say theta is in the bottom right corner. So what is sine of theta? What's opposite theta? 24. What's the hypotenuse of this triangle? 25. What's the cosine of theta? 7. Good. 7 over 25. What's the tangent of theta? 24 over 7. Good. And then the cosecant, the secant, and the cotangent, we just flip them. 25 over 24, 25 over 7, 7 over 24.
Wait, how did you know that was the angle that you...
I put it there.
Oh.
Yeah, I said I would put it there. It would be there.
And you were saying that this also works with the x and y, like it doesn't matter.
Right. Like if this would be written, that would be the question, would be given to you this way. But if you saw this as in, it said the terminal point was on, it would be 7, 24. The 7 would be the x, the 24 would be the y.
Right.
And you could do the same way. You could find r and then do y over r, x over r.
But I'm saying, but if it's given like this without the coordinate point, you have to use the Socatoa.
Right. Question so far? Okay, I'm going to put theta at the top this time. Is there a triple with 1 and 2?
Pretty sure the answer is no.
What, root 1? Yeah. So that is not a triple, right? So I could say that this is my x, and I could say 1 squared plus x squared equals 2 squared. 1 plus x squared equals 4. X squared would equal 3. X would equal the square root of 3. Now, normally that's a plus and minus square root 3, but we're not moving this around a circle. This is just a triangle, and a triangle can't have a negative length. So sine, cosine, tangent, cosecant, secant, cotangent. What would sine of theta be? Good. What would cosine of theta be? Good. Tangent? Good. Root 3 over 1, which is just root 3.
For Socatoa, would they be, like, in this case, would they ever be negative unless one?
And a triangle, no. So unless you have a coordinate point that you're moving around your circle, it's always going to be positive. So a standard triangle is always going to be positive. The only time you'll see an overlap in a little bit, like it will give you maybe a triangle and it will say that this lies in the third quadrant. Now it's going to change it. All right, so then cosecant, I'm going to flip it. So I'd get 2 over square root 3. Can I leave it that way? I have to rationalize this. So multiply by root 3 and root 3, and I get 2 root 3 over 3. Secant, I flip 1 over 2. That's 2 over 1. I can just write 2. And tangent, that's technically root 3 over 1. So this becomes 1 over root 3. And I rationalize. Questions on that one? So I will tell you that if let's say the square root was in the denominator over here, let's say that was 2 over root 3, and then I rationalize it. When you go to flip it to get to the cosecant, you want to flip it before you rationalize it. So you want to come back to here. Otherwise, you're going to rationalize something you already rationalized. So if you have something that's rationalized in my original trig functions, then before I flip, I want to go back to before I rationalize to flip it to get the other side. You'll see this in a minute, but I would say that's a good tip. Don't wait till after you rationalize it and then flip it. Go back to before. Everybody good so far? Yeah? Okay. All right, so there are 2 special rate triangles that hopefully you remember from geometry, and those are 30, 60, 90, and 45, 45, 90. These are also things that do not go away anytime soon for as long as you take math, except maybe stats. You will see special right triangles. Standardized tests love special right triangles, okay? So the relationship between a 45 when you're not in a unit circle where the radius is 1 is A, and A root 2. So any triangle that's a right triangle with one 45-degree angle obviously has another 45. Or any isosceles right triangle, because those are the same thing. Those are your relationships, A, and A root 2. Now the moment I put this triangle in my unit circle, it turns into 1, and root 2. Because the radius is 1, so does that make sense? The x is 1. So is the y. On a 30, 60, 90 triangle, in any 30, 60, 90 triangle, the relationship opposite the 30 is your A, opposite the 60 is your A root 3, and opposite the 90 is your 2A. Now the moment I put the 30, 60, 90 triangle inside my circle with a radius of 1, that A becomes 1, so I get 1, root 3, and 2. Which means I can now find all of these using those right triangles. So I can use these, eventually we're going to use these with a circle too, but I can find all of these trig functions of any of the special angles, meaning 30, 60, or 45, using those triangles. So if it is a 30 or 60 angle, I'm going to draw out my 30, 60, 90 triangle. This is now in a circle because I have a degrees. So it is opposite the 30 is your 1, opposite the 60 is your root 3, and opposite the 90 is 2.
So this is like what we did the last lesson with.
But you did it with an x and a y.
Yeah. And this is like, I guess like a more accurate way to find the 36.
It's just a different way.
I'm just guessing.
We only did it with the last ones, we only did it with the quadrant angles. So 0, 90, 180, 270, 360. Eventually, we're going to get into the unit circle where you'll learn more of these angles. But right now, we're going to switch back to the triangles. So I've got 30 degrees is in that bottom left corner, right? So if I want to find the sine of 30 degrees, I'm looking for the opposite and the hypotenuse. So what's opposite 30 degrees? 1. And what's the hypotenuse of this triangle? 2. Then I go to cosine. I want the adjacent over the hypotenuse, which is root 3 over 2, right? And then tangent, I want the opposite over the adjacent. 1 over root 3, which gets rationalized. Root 3 over 3. Everybody good so far? Now I flip them. So 1 over 2 becomes 2. Root 3 over 2 becomes 2 over root 3, and that gets rationalized. And then the cotangent, and this is what I was talking about before. I already rationalized that. So I don't want to flip the root 3 over 3 and then have to re-rationalize something. I want to go back to before I rationalized it and flip that, and I just get root 3. You would get the same answer doing it the other way. It's obviously just extra work you don't need to do because you're rationalizing something that's already been rationalized. All right, you find the 60s. So you do the sine, the cosine, the tangent, this cosecant, the secant, and the cotangent of now the 60 degrees.